So, welcome. Just going over some things that happened recently. Last Friday, we went to the University High School and had a star party with their astronomy club, which I think it's really cool that a high school has an astronomy club. I wish my high school had an astronomy club. And just helped them with their telescopes and observed some cool stuff. And there's a possibility that we can continue working with them and do similar events in the future. So be looking for that. It's if you've seen the XKCD, it's abusive astronomy. So just and moving on to events we have coming up. Biosphere 2, we have an event this Saturday, February 19th. We are working with the Bio 5 Club to kind of do a joint event, and because we met with them at the club fair, and they do things like, their outreach includes stuff like isolating your DNA and then all kinds of cool stuff. So we're going to try and do some astrobiology themed comet stuff so that we can relate like the whole evolution of life to any interested people. And if you haven't been, it's a lot of fun because you get to be at the biosphere and work there. Another smaller event, there are some Girl Scouts that are potentially interested in science and astronomy, and you know that's an important thing, getting girls into science and astronomy because there aren't as many. So if you want to be at Stewart, just in the lobby to help answer questions the February 25th, that would be greatly appreciated, especially if you're a woman, so they can look up to you and understand that there are women in science and engineering. So you can talk to me about that if you're interested. Another event that we potentially have coming up, Earth Hour, is March 26th, and it's a worldwide event where corporations and businesses and households all collaborate to just turn off their lights and all extraneous electronic devices for an hour, just to kind of show the importance and awareness of climate change. And we have an event at the university, and they will be turning off the lights on the mall, so that's a great opportunity to kind of bring out some telescopes and just join in the celebration of that. Then another event that we can possibly do, if there is interest, is Yuri's Night, and this is basically just a celebration of space and space exploration. It's actually, this year is the 50th anniversary of human spaceflight, when Yuri Gagarin first went into actual outer space. And there is a party, I guess, at the Pima Air and Space Museum in Tucson.
However, the party is on the 8th, right? Not on the actual date?
Oh, that's correct, yes. It's on the 8th, thank you. And there'll just be a lot of space-themed people there. It'll be a cool event, and it has been in the past. There's a possibility we could work on this. Unfortunately, I will not be here, Kevin will not be here.
I won't be here.
Lots of people won't be here. But if we have enough interest, we could definitely do something for Astronomy Club. So could you raise your hand just if you're potentially interested in the weekend of the 8th, doing something for Astronomy Club at this event?
That's Friday night. That's also the same time as the Boxer event that we're going to, and we're going to a booth set up at,
Okay.
just so you guys know.
So, anybody? Anna? Okay.
Few.
A few people. Okay, thanks. So, I think I asked this question last week, but there weren't as many people. How many here are actually doing research? So, if you are interested in actually presenting that research to a lot of people who are actually interested instead of your friends and family who are just way out of their interest range, we are planning a trip to the American Astronomical Society meeting in Boston this May, and it's a great opportunity to get contacts. And I know at the first meeting we talked about, we had quite a big presence at the last AAS meeting, basically over winter break. Camber, Kevin went, I don't know if there was, Jake also went, yes. And they will tell you it was a great experience. And if you are interested in coming to this spring event, meet with Kevin and I after the meeting so we can discuss potential funding so we can go as a group. Another possible event, previously we have gone to the 61-inch or the 90-inch to do eyepiece observing, just because it's really cool to do eyepiece observing on a 90-inch telescope. I don't think many people will be able to say that they've done that. And so these dates are open for TBS time, which means that it's still open to be scheduled. And so how many people here would be interested in possibly doing eyepiece observing? Excellent. That's great.
Are there any preferred nights? Because the 18th and 19th is the tail end of spring break. The 25th and 26th is the weekend after.
26th is the Earth Day, or Earth Hour.
26th is Earth Hour, so we'd probably do it the 25th or the last weekend of spring break.
25th? Wouldn't be bad. Okay.
Okay, we'll try for the 25th then.
Just going over again all the projects we have going on. The Extrasolar Planet project, we have things happening. They meet 6:30 p.m. on Thursdays in the computer room downstairs. There's a binocular telescope project. And when is that meeting, Blythe? Or
That's
Wednesdays at 3. And also, for all the trips that we talk about going on, we have all these kind of cool outreach materials. Like, I think this week we're designing a way to kind of simulate a comet. If you want to be a part of that process, meet 3 p.m. is in the club office. Also, potentially, last semester we did a radio project and it got published, and from what I hear, there's possible interest in doing that this semester.
Next semester?
The radio project, so our data, it has been used in certain people's projects, but we might need to do some follow-up stuff. I don't have complete details, but is there interest in continuing a radio project this semester? Show of hands. Okay. And I will talk to the powers that be, and things will happen.
Okay, just to go over for anyone who doesn't know, that we have a club office in the trailer just north of Stewart. It's a good place to just hang out and do homework if you want, and it's also a lot of place where club events go on. And there's a schedule posted on the door of all the events that we have going on this week. So if you're ever curious, you can look at the schedule. Also, that schedule is posted online, so all kinds of ways to access it. Last thing, I think, is the astronomy question of the week. Is held every Friday at 4. Last Friday, there was not enough people there, so it got postponed to this Friday. And so we're talking about orbits. So if you're just kind of interested in talking about astronomy concepts in a thought-provoking way that you can understand the what's going on. It's a great place to be. And just one last note, membership dues are $10 a semester to kind of support all the projects that we have going on. And if you have not filled out the membership form, please do. It helps us keep track of what's going on. Who's in the club. And happy Valentine's Day. It's the Rosette Nebula, and that's just a crater on Mars that looks like a heart.
There's also a heart nebula.
I think I showed
that last
I
week,
showed
yeah.
last week. And so now, as promised last week, is Blythe Guvenen.
So this talk I'll give is going to focus on research I did with the 61-inch telescope on an AM-CVN star. I'll talk about what that means. And it was initially observed by the Kepler satellite, which is a space observatory in orbit. And we took spectroscopy with the telescope and determined several characteristics and confirmed many observations by Kepler. So I'm just going to talk about what we did and a little bit about the star. So our star is called AM Canum Venaticorum. It's Latin in the constellation Canis Venatici. It's near Ursa Major, which is the tail end of which is right here. You don't really hear much about it. It's just a really not very obvious set of stars here. It's Latin for the hunting dogs, and it's circumpolar, which means at our latitude it goes around the north star. So an AM system is a binary star system, two stars orbit one another. And AM refers to the star spectral classes. So one is spectral class A, which is sort of the main sequence star, and the other is spectral class M, which is typically white dwarfs and stars of that nature. So these are dependent on the temperature and luminosity of the stars, and also determine the spectral signature of the star. So we were observing what was called a cataclysmic variable. And cataclysmic variables are stars that have an accretion disk around them of plasmic material from another star. And it's called variable because it varies in luminosity and temperature over time. And cataclysmic means that it's sort of unpredictable. So you may get a large spike or a certain mode of pulsation from the star, and then it might not be exactly uniform or regular over time. And so yeah, it has a white dwarf, which is our star, and a compact main sequence companion, which it was sort of feeding off of, stripping the atmosphere off. So white dwarf accretions form because when there's two stars in a system, they'll rarely have exactly the same masses. And so what that means is that they're going to have different lifetimes. A star's lifetime is determined by how much hydrogen it has and how quickly it burns through it. If it's a very massive star, it'll have a lot of gravity, and the gravity will accelerate the fusion, and it'll die more quickly, usually more violently. But there's also stars that die as a white dwarf, and that's when it sheds its outer layers and becomes just the hot exposed core of the star that is supported by the electron pressures between the atoms of helium and hydrogen. And the electrical repulsion is because like charges repel each other, and there's enough gravity to overcome that. If there is enough gravity, the protons and electrons in the atoms merge into neutrons, and you get what's called a neutron star. But in our case, the star wasn't massive enough to do that, so we have one main sequence star that's still living out its life, and then one white dwarf star that is feeding off of it. So here's what it would look like. It's an artist representation. Here's the companion star, and here's the cataclysmic variable. So here's it's like a ribbon of plasma. They're probably not this close in actuality, but this disk of material is the accretion disk that's forming around the companion star. So the star was sort of unremarkable at first. It was part of a survey by the Kepler satellite, and after initial review of the spectrographic data, they realized that it could be a compact pulsator, which is a compact star and a pulsating white dwarf next to it. So when there was follow-up observations done and ground-based observations like the ones we did, we found out that it was helium-dominated, and this suggests that it is a helium-rich white dwarf. And we also confirmed many Kepler observations and also discovered several other characteristics about this object. So white dwarfs are helium-dominated because most of the hydrogen is burned through, and so a star might be 99% hydrogen, helium rich stars are 10% or more helium composition. So the spectrum of the star we were looking at was reddened by interstellar absorption. And what reddening is when you have a very short wavelength. In this case, our star's wavelength is closer to blue. Very short wavelengths have a shorter period, and so those are more likely to bump into something like an interstellar dust grain or an atom of hydrogen or helium in a dust cloud. And a very long wavelength, it won't be scattered as much because there's a lower probability of it colliding with something. And so what you get is, say there's a hydrogen atom in the way, the photon will strike the hydrogen atom, excite one of the electrons, it'll go up an energy level, and then when it jumps back down, it emits a photon of light that's redshifted. So we have to sort of adjust for that in our observations. So the way the star its orbit was set up is that there are two ellipses that are orbiting around a common focus right here. And Kepler's laws, they sweep out equal areas in equal times, so they'll go very quickly around here for a greater area, and right here for this star, and they're going in opposite directions. So they can orbit in various ways. Sometimes they orbit a common center of mass like a planet like Pluto and Charon, but in this case they have a very kind of cool looking orbit, and I can show you what it looks like right here. So a little computer animation done. I'm not sure exactly which system it is, but this is essentially what the star is doing. So here's the compact companion, and here's our star. And so it swings out a very long way. The focus would be somewhere in here. And then, boom, they come really close, and then really far. And so what will happen is the accretion around this star will accelerate when it comes close to its companion, and then slow down when it moves further away. So, yeah, that's essentially what I just said. And then you get a spike in luminosity or magnitude of the system when the stars are close by. So this is the data we took. This is amplitude as a function of frequency. Here's the companion star, pretty even spread of frequencies. Here we have a spike in this frequency here, which indicates helium, so that's how we know the star is helium rich.
Question, Mike.
What's that?
Can you actually see the two stars then?
The two stars actually cannot be resolved at the distance and size they are close to one another. So everything here is inferred just by the spectral characteristics of the system. But we know because there's the pulsations that it has to be feeding off something, so we assume two stars. And the modes of pulsation are that it can't be any more than two stars. And here are here's the actual optical data we got. Over this time, the relative amplitude looks like this. So there are many different modes of pulsation here. Some are a little bit more chaotic, and some are very regular. So here's the spikes. These actually correspond with the star's orbital period, and these are different dates. You can see here that the observing might be a little worse, or it might have some atmospheric interference, but we can definitely tell that they are pulsations, which is the main thing. What's that?
How long does it take them to orbit each other? I'm going to talk about that now.
So, yeah, the orbital period of the system is roughly 950 seconds. Wait. That's not right. Sorry. The pulsations were roughly 950 seconds, not the rotation. Orbital period. I don't actually know what the orbital period was. So what we found was that the mass transfer from the compact star to the white dwarf was a very small amount, obviously the total mass, so 8.5 times 10 to the, actually that should be -9 stellar masses per year. And we also found that the accretion disk angle was about 10 to 20 degrees from the horizontal in the line of sight we were looking. We also determined the pulsation period of the system to be roughly 950 seconds, but there are several pulsation modes observed, and it isn't always regular because it is cataclysmic and variable. And then we determined the actual distance of the system to be between 250 and 330 parsecs, which corroborated with what Kepler found. And so here are my collaborators, Fontaine, I forget his first name, from the University of Montreal, Betsy Green from this college. Here, Caitlin O'Malley, she was my observing partner. And I also got some of the illustrations from the Harvard Department of Astrophysics. So that's all. Any questions? Yes. Okay, Carmen.
I was wondering, can you determine orbital physics since you can't resolve?
I think that's why the paper was silent about that. I don't think there's any way really to know, but it can be inferred from
What if you're related to
the
the
yeah, it would be so, but we can't tell which pulsation modes are when the stars are close to one another, or if the star is going through some random spike in luminosity because it just happens to, I don't know, some more mass falls in more quickly for a split second, and then it goes back down to a lower state. Okay, anything else? Jake, you had your hand up?
Yeah, you said you observed spectra on the 61.
Yeah.
What instrument do you use for that?
I think we did D, V, and I filters on that. So.
Yeah, I thought all the spectroscopy was on the 90.
There's no spectrographic on
Okay, some of that data may be from the 90-inch that was incorporated in. It was a lot of ground-based observations from a lot of different people. That probably was a misnomer in there.
Okay.
All right. Anything else? Okay, thank you.